Okay. Okay, hey guys, like the lecture video you guys watched, we're going to be doing a lab here on a split phase motor. Okay, with these split phase motors, we have, for this one, we have two windings. We're going to have a start winding and a run winding. Our start winding is going to be high resistance, low reactance. Okay, so high resistance. These windings are going to be smaller in size, low reactance. They're going to be closer to the surface of the stator. Okay, our run winding is going to have high reactance, low resistance. They're going to be a larger wire, and they're going to be deeper inside the stator core, okay, to give us a higher inductor reactance. Why is that? Well, as was mentioned in the lecture, we need a means to create that rotating magnetic field that is the same as we had with our three-phase motors. So to do that, we are going to take advantage of these two different power factors we've created on our run and our start winding. So if we have a look here, our run winding, this longer vector here, it's got the high reactance. Okay, so if we have a look at it with reference to our supply voltage, it's going to be the furthest out of phase from our supply voltage. Now, our start winding is going to have a low reactance, high resistance. It's not going to be as far out of phase as our supply voltage, but it is going to have a range between 30 and 50 degrees from the other winding. That's critical for our rotating magnetic field. Now, this is what the waveforms are going to be like. So when we're talking out of phase, we have our voltage waveform here that's going to be typically whichever the size of the windings are going to be, or the reactance of the windings are going to determine that angle and how far out of phase they are. So then we have our start winding here, which is actually going to be closer to in phase with our supply voltage, and then we have our run winding, our blue dot here, which is going to be further out of phase. Okay, now we're going to first thing we're going to do is we're going to start the. Okay, guys. First step in this lab, what we're going to do is we're going to see what happens if we don't use our start winding. We're going to connect our 120 volt supply to our run windings and start it up. Okay, let's have a look and see what happens. Hey guys, okay, now we have our capacitor, our split phase motor here, okay, wired up, the run winding only, connected to our single phase 120 volt power supply, which is actually set to 100 volts here. We have an ammeter in series, so we can see what the current jumps up to while we're starting. Now, when we start this up, our rotor should not move. Okay, we don't have an established rotating field yet. That second start winding isn't in the circuit, so let's give it a try. All right, voltage is a little lower than 100 volts. No rotation here. We're at a little over 10 amps here for our line current. Okay. Okay, hey guys, we have our run winding only connected, and one of the problems we have is our start winding. We don't have any means to start our rotating magnetic field. So what we're going to try now is we have our run winding connected. We're going to start it up, and our rotor's not going to turn. I'm going to give it a little kick in one direction to get it up to that 75% or higher full speed, and once it gets up to that point, the run winding should be sufficient to keep it running. So let's give that a try. Also, keep an eye on the current there. At startup, we're going to be a little over 10 amps, and then it should drop down. Okay, let's try this again. Okay, nothing going. Current is at 10 amps. Current dropped down quite a bit. Motor's running. And it'll keep running until we shut the power off. Well, let's shut the power off. Okay guys, now what we're going to try is we're going to connect our line to our run winding as it is here. We're also going to do a connection to our start winding, but we're going to bypass the centrifugal switch. So why we're doing that is we want to see what the continuous running current would be with the start windings still in the circuit. Now remember, the FLA for the run winding is going to be 4.6 amps because we're assuming that once it's up and running and it's doing work, our start windings aren't in the circuit. So for this winding itself, its maximum current is going to be 4.6. Okay, let's have a look. Okay, hey guys, now here we have our split phase motor here wired up. What we've done is we got our single phase supply. We ran it through two ammeters right here. We got one to monitor our run winding current, the other to monitor our start winding current. Okay, and then our run winding is the top two here. We have that going through and connecting up to our run winding. Then we have our start winding down here. We have our centrifugal switch, again, not connected. So we're going to keep this run winding in for the full duration of its operation now. Okay, so I'm going to give her a start. Okay, now, pretty quick startup for this motor. We're running at full speed. Our start current is, on the 8 amp scale, it's about 7 amps.
It just tripled.
Okay. Okay, hey guys, now we have our split phase motor wired up. We got our run winding and our start winding. We are not incorporating our centrifugal switch because we want to see how much current we're going to get if this start winding is kept in the circuit. In series with our run winding here, we have an ammeter, so we can monitor what the current's going to go up to, and in series with start winding, we have another ammeter monitoring its current. Now, keep an eye on it. These are going to jump up and going to get a little high at startup, but our start winding here, keep an eye on that current. That's the one we want to see what happens. Now, the start winding has, or also called auxiliary winding, has a overload in it, so it may trip after a few seconds. The maximum current for the start winding is 2.5 amps. So, okay, we're going to give it a start and see what happens. And I might talk a little quickly, so if in case it overloads. Okay, we're at about 7 amps in our start winding. Our run winding is about 5 amps. Okay, it's going at a good RPM. And the overload just tripped. Okay. So since the overload tripped, and the motor's still going because the overload is in series only with our start winding. Our run winding is keeping it going. Okay guys, now we had our motor connected like so, and we started and stopped it with no load on it. We didn't have the belt coupled up to it. Now we're going to connect the belt up to the dynamometer, and the dynamometer is a method on how we're going to add load to the motor. Okay. Also, at this point, we're going to incorporate our centrifugal switch into the circuit here. Okay, so what's going to happen during startup, both coils are going to be energized. Our start winding is going to actually help get the motor up and turning. It's going to help create the rotating magnetic field until it gets approximately 75% full speed. Our centrifugal switch will open and take the start winding out of the circuit. So right now we're going to start it up with a moderate load and see what happens. Hey guys, now we have our split phase motor here wired up. We incorporated our centrifugal switch. Okay, so we're going to start it up. The current for the run winding, it's going to hover just under 4 amps. It's connected now up to our dynamometer, and which is going to give it a moderate load. So it's not on. It is started right now. It's at a lower setting. We're going to see what happens. How this guy's going to start up. Inrush current. So our current is about 3.8 amps. Okay. Our load is pretty low on this right now. guys, now I'm going to increase the load here on our dynamometer. Okay, still got a moderate load. I'm going to get our current up here to close to full load amps. Let's see what happens. You can hear the motor working now. Going over 4 amps. 4.2. 4.4. Okay, here we're about 4.5 amps right now. 4.6. Okay, now we're running at full load amps, 4.6 amps. And we got pretty well, this is what we call full load on the motor. Okay? Now we're going to start up our split phase motor here under full load. Okay, it's not going to start and it's not going to turn and get up to full speed because the angle between the start and the run winding is not high enough to achieve the amount of torque we need to start at full load. So let's have a look. As you see, it struggled and right away it tripped out the breaker here. Okay, so the overcurrent protection is preventing us from keeping the motor going. Okay, hey guys, now we started this up. We noticed not very good for starting under full load. Okay, so what we're going to do now is add a capacitor in series with our start winding. Okay, so you see here, we have our supply coming down, so we go through our start winding, centrifugal switch. Might not be in the exact same spot as on the lab, but electrically that's the position, and then now we have a capacitor in series with our start winding. What's going on there? Well, this capacitor is sized large enough that it's going to give us a leading power factor. So here's our supply volts, here's our new starting current. Okay, so the winding in our start circuit here, it's going to have a leading power factor, the current now. Our runs power factor and current, that's still going to be the same. So when you look at the waveforms here, we're going to have our start current is going to lead our our voltage, or supply voltage. And this angle, the goal is to get that to 90 degrees. Okay, so that's going to give us the optimal amount of torque for starting. Okay, hey guys, now we have our split phase motor here where we got our centrifugal switch in series with our capacitor, and that's going to be in series with our start winding, auxiliary winding here. So when we start up our motor, once it gets up to its 75% full speed, the centrifugal switch is going to take the capacitor and the start winding out of the circuit. Okay, also remember that when we had the regular split phase motor without the capacitor in it and we started it under full load, it wasn't able to get up and going. So those type of induction run, resistance induction start motors are not very well suited for high torque starting applications. Now this capacitor start resistor induction run winding, it's a lot more suited for a lot better starting torque. So we're going to start it up right now. This is under full load. We haven't changed the load setting from the previous labs, and we're going to see what happens, where it's pretty well stalled and tripped the overcurrent protection before. Now let's see what happens. Okay, we got our full load, and as you notice, our start winding, it peaked up. Once it's got up to 75% full speed, centrifugal switch dropped it out of the circuit. We're going to have a look at it one more time. Pay close attention to the start winding. It goes pretty quick. Okay, here it goes. Okay, it was that fast. Went up, then kicked off right away. Because we have a very high amount of torque with the capacitor in the circuit, so it's going to get up to that predetermined centrifugal switch speed a lot faster. It's got high enough torque to do that. Hey, hi guys. To quickly summarize what we just saw, first step with the lab, we had our run winding only, no start winding in the circuit. We had to give it a little help to get it up to full speed, and then once it got up to the full speed, it would keep running. Second part of the lab, we put our start winding in place, and we had it connected so they both energize at the same time. That started our motor rotor rotating, so that worked. But the current, it was really high and it stayed high, so we don't want that. That's not a desirable thing. Okay. Next step, we incorporated a centrifugal switch. Okay, where we had both run and start windings both in the circuit at startup, and then once the centrifugal switch got up to 75% full speed, our start winding was pulled out of the circuit. Problem we had though is if we put full load on this motor and tried to start it, it wouldn't work. So this type of, without our capacitor in the circuit, this type of configuration of motor is not well suited for applications where we need high torque. Then the last step, we put our capacitor in the circuit. Now our power factor angle for our start current is leading our supply voltage. So our angle between our start and our run is pretty well almost 90 degrees, if not exactly at 90 degrees. So we had a very high amount of torque for startup. So we started the motor up under full load, and it was able to handle that full load. And then again, the centrifugal switch dropped the capacitor and the start winding out of the circuit once it got up to near full speed. Awesome, thank you.